Good afternoon. On behalf of Engineers Australia, I'm delighted to welcome you all to our Thought Leaders series, Future of Stormwater Storage. My name is Amanda and I'll be your host for today. Firstly, in keeping with our custom, Engineers Australia acknowledges the traditional custodians of the country throughout Australia and recognises their continuing connection to land, waters and community. We pay our respects to them and their cultures and to elders past, present and emerging. Before we get started, I'd like to acknowledge that today's webinar is being hosted with Engineers Australia's industry partner, ECHO. ECHO in Australia offers an extensive portfolio of stormwater, building drainage systems, cable pit and ducting systems, access covers and other niche products. The company has celebrated 25 years as Australia's foremost manufacturer with facilities in Western Sydney, New South Wales. ECHO take pride in providing excellent customer service and extensive technical support from specification to the finished product installation. Today we will hear from two speakers followed by our live audience Q&A, and I encourage you to send questions through to our speakers via the YouTube chat box. I'd now like to welcome our first speaker, Troy Eales. Troy is the Water Resources Lead at Calibre Consulting, a specialist civil engineer with over 18 years of experience. As team leader for the Water Resource team, Troy is involved in stormwater management for residential subdivisions, land development projects, commercial and industrial developments, including but not limited to stormwater quality and quantity, flood studies and water balance modelling. Troy's technical expertise is in water-sensitive urban design, as well as hydrological and hydraulic modelling, encompassing the integration of 1D and 2D modelling. Please welcome Troy Eales.
Thank you, Amanda. Yes, my name is Troy Eales and I am the Calibre Water Resource Lead. My team and I predominantly deal with flooding and stormwater management. One of those aspects of stormwater management is stormwater storage. That's what I'll be talking to you today about, particularly looking at the underground storage and the options around those. So to start with, I'm going to go back to why do we need storage? We start with the fundamentals so we can all be on the same page. I will then quickly move on to the types of storage, the benefits of below ground storage, some of the considerations when you're selecting the type of storage. I'm sure we've all seen the water cycle going back to the days at school. And really, nature was really in sync. We'd have rainfall that infiltrated and fed our vegetation, runoff went to our creeks and rivers and entered our surface water, evaporated and the cycle went. As I said, nature was very in sync. And then we introduced humans. Probably more realistically, as we started to progress, we started to replace some of the vegetated pervious areas with these concrete jungles of hard surfaces. Suddenly stormwater became problematic, and our solutions traditionally were about getting water away as quickly as possible. So we introduced concrete pipes, concrete channels to really get that flow away. But really all that did is increase some of the volumes, increase some of the flows and velocities, and sort of poorer water quality for our receiving waterways. So while there is a need for concrete pipes and channels, we also had to think outside a little bit, be a little bit more creative on how we manage stormwater. And that's when sort of stormwater storage became its own. There are a number of storage types. We'll be focusing on detention, retention, and infiltration. Stormwater detention is really an effective means for managing some of the flooding and excess stormwater flows. It really is only a temporary storage of stormwater during the storm event that's then released at a controlled rate. Essentially, think of it as a bucket with a hole in it. If the hose filling up the bucket has a greater flow rate than the hole, then the bucket starts to fill. And that's our detention, our temporary storage. And as we start to shut off the flow that's coming in, we start to dewater and empty that storage. So this is sort of demonstrated more on the hydrograph here, which is just a flow versus time. So we have the blue, which is the natural or pre-developed scenario. We have just a little steady rise in flow that sort of peaks at one point, and as the storm starts to decrease, it starts to flow away a little bit more. Suddenly, when we introduce our impervious areas, we have this red graph, which is very much more aggressive, steep climb to a much higher flow rate. And then once again, a very steep degrade. And the detention focuses on managing these flows above that existing flow rate. So that grey area, that storage of the excess flows. When we start to look at stormwater detention, we start to get hydrographs that are closer to the green, where we still have a steep rise, but we hold it off at a capped off flow rate that's closer to the natural development. There is a longer lag as it starts to dewater and empty that excess storage, but then we have a gradual decrease once again. Now, these requirements for detention, they're often set by our consent authorities, whether that be state or local councils, and they're typically around some of the best practice. There could also be a regional strategy for a creek catchments, for instance, which might specify the types of storages or types of detention requirements we have for that specific catchment. Essentially, but most of the time it's around the best practice of not aggravating the existing peak flow rates for all storm events. Now that can be up to the 100 years. So it might mean the need to have a number of outlets to match each of those minor storm events and upwards. Alternatively, there might be a need to overcompensate some of this detention to match an existing capacity of a pipe network downstream. Often they were put in back long before a lot of these impervious areas, so they may not have the capacity to deal with some of the newer catchments and newer developments. So it'd be about overcompensating some of that detention to match that. We can sort of calculate this on back of the envelope sort of calculations, detailed spreadsheets, but more times than not, it's usually the hydrological and hydraulic modeling that's used to size this. So that's about a matter of just representing some of these pre-developed and existing catchments and determining the flow rates for those, then seeing what would happen when we increase these impervious areas. Then we hydraulically model these tanks and outlets and sort of trying to mimic some of those existing peak flow rates and size these detention systems. Alternatively, some of the local councils may have already done some of the heavy lifting with the modelling, and they'll be able to provide you with a site storage requirement or a PSD, which is the permissible site discharge. So that's typically will tell you the volumes and the flows you're allowed, and it's shown as a per hectare of site area. It's important to understand that with detention storages, they really need to be free draining. They need to empty as the storm finishes, so they're ready to go again, and they've got that active storage before the storm event starts. An alternative storage is retention. Now, retention doesn't replace detention. It more isn't part of the overall water cycle management. So that's the holding of stormwater for the reuse. And this is to meet some of our reuse demands, also manage some of the volumes. So once again, the requirements are often set by authorities, which will specify minimum volumes that need to be met, and that will be in line with some of the best practices. There could be a regional strategy that's developed for that catchment that will specify those. But more times than not, again, it's defined by the water demand. We can often be quite forgetful in these times of heavy rainfall and flooding, of just not long ago that a lot of us were under quite tight restrictions. The dam levels were down. We just didn't have the water supply to meet some of our demands. And that's where the water retention really comes into its own. It's about understanding those demands and supply and matching that up. And that's probably best done by a water balance. It can be in spreadsheet form, but also your music and other modeling programs are best suited. They're about modeling some of those rainfall and the distribution of those rainfalls, understanding the catchments, and understanding those demands and what reuse and storage is required to meet those demands. The key to any sort of effective water balance and sizing of a retention is really understanding the reuse and the uses. So a lot of the time we look to harvesting and irrigation as a reuse, and they are an effective reuse, but the catch-22 is when we have the most rainfall, our storages are full, is when we don't need to use it for irrigation. So it's best practice to have alternative methods which aren't weather dependent to be compatible with the water harvesting style of things. So that could be your toilet flushing or your laundry uses, your commercial and industrial uses. Also, the retention of stormwater is also part of that treatment train. So we look to try to remove some of that volume, and along with that comes some of those pollutants attached, so they can help hit some of those water quality targets for our receiving waters. It's really important to understand that while OSD or detention is all about managing those excess flows, retention is about trying to manage those volumes, trying to remove some of the volumes that have come from those additional hard surfaces and trying to mimic some of the environmental flows that our receiving waters receive. The third opportunity for storage is infiltration. And it really is an effective way to manage flows, volumes, and also some of the water quality. It's just the storage that holds the storage while we promote the infiltration into the soil. It recharges the groundwater, but also starts to try and mimic some of the impervious areas of the natural catchment by introducing the water back into the environment and filtering through that way. It's important to understand with the infiltration that it's not suitable for all environments. For your soil types that have a very low infiltration rate, such as your clays, it really doesn't work very effectively. There's no sort of drainage through those soils. Alternative, will your saline or sodic soils, it's really not a great opportunity to promote infiltration. It's better to keep the surface waters and the ground waters separate in those scenarios. When we think of a lot of stormwater management, we do envisage these large regional basins at the end of the line. And while they're very much an effective place for the regional treatment, it's often hard to find the land areas that aren't heavily constrained that these sort of storages do require. So the introduction of underground at source storage really does open a whole lot of new possibilities. It allows us to have multi-uses for the stormwater management. They can be within the building surface footprint itself. They can be in the basements. They could be underneath an open space area. It also doesn't have to be all below and all above. So there can be the combination of the two. So you can have your nuisance regular storm events being contained within an underground storage that then can just overflow into a multi-use above ground for the more rare and high storm events. Overall, our below ground treatment can form part of this overall treatment train. It can be combined with some underground pre-treatment or alternative methods and form part of that treatment train to achieve some of the water quality targets. The other advantage to the below ground, they're a very known area. The square sides and equivalent volumes can be calculated quite easily with no changing parts. There's no degradation of batters. There's no vegetation which could sort of absorb some of this active storage area. So they're very known, sufficient, no changing solution. They can also work quite efficiently in the design and work around heavy constrained sites. So they can be shaped accordingly and work within the tighter, more constrained areas that the open above ground methods possibly can't get into. They're also out of sight, so there's no unsightly devices that may be due to the poor maintenance or vandalism. So by having less public access means there's less damage and less safety risks, but also less damage from some of the extreme events like high winds and things like that. With stormwater management, we often do look to try and mimic some of the natural environments, but these can create habitats for wildlife. In some areas, that isn't quite the ideal. A lot of cases that might introduce pests. You'll often hear about the bin chicken habitats forming in a lot of these stormwater management systems. You might have heavy foot traffic where you don't want to promote dangerous or potentially venomous animals to be within the region. Also too, if you're working around or along an airport or around a flight path, for instance, you may have regulations not to promote bird life because of the fear of interaction with the planes. So there are solutions of putting these storages underground, so just avoid the need for wildlife habitat. And lastly, a lot of with these regional basins, they are quite timely, and they often the development is ahead of them. So there's the need to provide temporary solutions. So the underground storage means that we can progress with the development while not having to, and also achieving the water quality targets in a temporary nature. There are a lot of considerations when coming to design and pick what sort of storage to go with, and it starts well before the design. So you're going to start to think about some of these levels, specifically with the detention basins. They really need to be free draining. So these outlets, although underground, need to eventually see daylight or connect to a system. We need to really think of the hydraulic constraints. Is there backwater that could be affecting the performance of these issues, and design around those? And while we talk about potentially having underground storage combined with basements or under building footprints, we really need to consider design for failure. So having these emergency overflows in the event that the outlet gets blocked or the system fails. We can't have damage to buildings or potentially risk of life. So we need to incorporate those well early in the design. We also need to consider what is above or surrounding. What's the soil mechanics? What's the groundwater like? What sort of structures are above? And that really leads into the design of the structure itself. When you consider the materials, not just in terms of strengths, but in terms of the environment. Are they environmentally friendly? Does this material suit this environment? And then move on to consider whether there's some precast or modular opportunities that we can use. The multi-use is really the advantage in the underground systems. It's how can we combine these detention, retention, and water quality structures in the one unit, and potentially what other uses can we have? So really maximizing our area. And then finally, really need to consider that these ultimately need to be approved, and what are the standards and requirements that we need to meet. So prior to going down any track, we need to understand what the finished product needs to achieve and what needs to be approved for exploring. In the design, we also need to consider construction early on. So we need to understand the methodology and how can we work around that. Well, what area do they have to work with, and how can we make it easier for the ultimate construction? Are there lightweight alternatives which can really limit the sort of machinery required and make it a lot safer for those workers? And consider access to this site. A lot of these sites are very constrained, and understand how we can design to make this easier to access and construct. And then ultimately, we need to start to really think about the operational phase and start to consider what will be the lifespan of this design when we're selecting a unit. And then consider, when is this storage going to be online? A lot of the construction processes, and specifically the construction sediment, can often be detrimental to a lot of these stormwater systems. So think hard and fast on when this unit will be online and what sort of measures we can use to protect the unit during the construction all the way through to its operation. And that leads us on to maintenance. You really want to minimize the need for maintenance, and that might require some pre-treatment of gross pollutants and coarse sediments prior to the unit. And this, but ultimately, it's not avoidable. You really need to have the design for access, but think about how can we minimize the need to access into the unit potentially. What machinery is required, and how can they get in there early on into the design? And ultimately safety. We think from the construction perspective, but ultimately end user. How can we avoid people having to enter this and avoid public? How can we think about potentially the inlets and outlets and how the public safety could be affected by that? And finally, consideration is more heavily is on the certification. We think about how this is going to operate and how has this been constructed, and how ultimately someone has to put their name to it. So you really need to be confident with both the operation and construction of these units. A lot of the precast and available products online have had vigorous testing. So by all means, critique that and use that to your advantage to understand the units that we're going to be putting in. I might leave that there for now, and I'll pass over to my co-speaker, Greg, who can talk more about some of these specific types of units, in particular, the geocellular type of units. Thank you.
Thank you, Troy, for your presentation today. I'd now like to welcome our second speaker, Greg Facey. Greg Facey is the Market Segment Manager for ECHO and began his career with the organisation back in 2004 as Queensland Specification Representative, providing education and project solutions to many state authorities, engineering and architectural firms. Greg progressed into the current market segment role, providing education, CPD support, technical advice and design brief development nationally to industry associations, transport authorities and designers in the stormwater management space. Please welcome Greg Facey.
Okay, thank you, Amanda, and hi everyone, and welcome to our presentation today on geocellular stormwater tanks. So before I start, I just wanted to thank the EA team for all their help in making today's webinar possible. And over the next 25 minutes, I'm going to describe the role of these plastic tanks and their characteristics and offer you a guide on how to specify them. Underground tanks are used in a lot of projects as councils legislate to protect their downstream waterways and infrastructure. Managing both the quantity and the quality of water being discharged off a site is only going to grow in importance, and particularly as our cities urbanise and rainfall events intensify as the climate changes. And these days, large areas of the built environment is being covered by impermeable surfaces, which of course increases the risk of flooding. Tank solutions are a conventional way to store and slow down the surface water runoff to pre-development rates, as well as replenish the groundwater at a more natural rate. So these are the system elements that are designed to work with the natural water cycle. On a slab or a pavement, drains are typically positioned to intercept or collect stormwater runoff, which is then treated or cleaned to prevent clogging or contamination downstream. And as you can see on the image, there are a number of tank solutions available to engineers and urban designers, both natural and engineered structures. Some of the engineered tank solutions include cast in place, precast concrete tanks, arches, and plastic structures. But today we'll focus on just plastic stormwater tanks, which can be easily integrated in a stormwater management plan for the infiltration, retention, or detention of the surface water runoff. The detention systems, which are also known as attenuation systems, are designed to spread the peak flow of a storm event. It does this by holding and releasing stormwater slowly, and as I mentioned before, the idea of this by controlling the runoff to reduce the risk of flooding downstream from a development. A retention system collects and stores water permanently for reuse, for example, to water landscaped areas. Infiltration systems, or soak wells, are used a lot in sandy areas to temporarily store the water to allow it to naturally seep back into the ground to replenish the dropping water table. So to illustrate this, retention and infiltration are two common adaptations of these tanks to make the best use of captured stormwater. Retention, so it can be used for irrigation or reuse purposes, and infiltration, so this is where the soil can naturally free the water from its impurities. But in both cases, the water is used at or close to the source of collection without it flowing through any downstream infrastructure or receiving waterways. But if you are discharging into a downstream infrastructure is the objective, then as I explained before, detention gives designers the greatest control over the quantity of water to enter it. In simple terms, it's an easy calculation. So before I go on, I just want to make a special mention of two types of hydraulic control structures. First are stormwater treatment devices, and these are located upstream of the tank, with their performance being individually assessed and governed by the EPA and the local DA requirements. And depending on the project requirements, there are many types, from gross pollutant or silt traps, stormwater filters, to even light oil separators where hydrocarbons exist. The other type of hydraulic structure are flow control devices, which, as the name suggests, control the release of water at prescribed rates downstream of the tank. These are typically installed in chambers with either purpose-designed mechanisms or just a conventional orifice plate. Now, both of these hydraulic control structures are not the topic of today's presentation, but I wanted to at least mention them as they are essential elements that affect the quality and the quantity of the water being discharged off the site. Now, I want to go back to this slide to give an overview of the storage options available. So from the top, we've got a detention basin, and you often see these in low to medium density areas. They tend to take up space that could otherwise be used for urban or commercial development. Next are concrete tanks. They are normally expensive to construct and transport just by the nature of the weight and the size. Next along are plastic arch systems, which require a decent amount of space. And finally, plastic tanks. And within this large category is a huge range of options, with not all being equal though. So today, I'm going to focus on plastic tanks that can be assembled into producing underground cells for water storage. And these can be adapted in a softscape where infiltration can be achieved. And here you can see them being assembled, wrapped, and then backfilled. But they can also be installed under slabs in commercial and industrial applications where the space is at a premium. In fact, geocellular tanks are installed in lots of projects, from car parks, driveways, in landscaped areas to commercial buildings, industrial areas, airports, and military bases. So in a recent installation, here is an example of a tank being used for infiltration for a surf lifesaving club. Stormwater capture from the club's roof and its infiltration into nearby vegetation was part of the sustainability design brief. With limited space to work with, designers needed to maximise the storage capacity of an infiltration tank while fitting it into a very restricted space. An easy to maintain full bay sedimentation trap was also required. Here's another example, and this is a tank being used for both infiltration and detention in Canberra. And the purpose of the tank was to manage runoff from the car park. Two different tank systems were installed adjacent to each other to work in series. One was an infiltration tank and the other was a detention tank. So in the industry, there is a wide range of options for plastic tanks. The two on the right are typical of what we would call a plastic crate system, and the one on the left is typical of a modern geocellular unit. I'll start with some general comments around these systems. So unlike concrete tanks and plastic tanks are quite versatile. They can be cut and joined, and the structure can be readily used for infiltration. Good designs have high void ratio and can connect to large inlets and outlets that can be easily inspected. Good designs are also load rated to hold their strength over time. But there are plastic tanks that are poorly designed, poorly manufactured, and difficult to access, monitor, and maintain. And unfortunately, these give all plastic tanks a bad name. And finally, the engineer has a responsibility too here. Despite the design or the maker of the tank, products always run the risk of being poorly integrated in a stormwater management plan. So when specifying plastic tanks, there are a number of things to consider. Councils, through their development control plan, will enforce compliance to regulation. They will specify the methods an engineer needs to use to ensure the property meets the stormwater management plan. And this takes into account the volume of water the property needs to manage from the landscaped or the hard stand or the roofed areas. But not only does a certifying engineer need to integrate the tanks properly, but as all key stormwater products, the structures themselves need to meet minimum strength, durability, and quality requirements. But in Australia, there's no standards that actually govern plastic tank systems. And the problem with that is that some manufacturers make claims about strength and design life that really just aren't substantiated. However, there is a UK standard called SIRIA, which is specifically written around geocellular tanks. It gives guidance on testing, structural design, construction, and installation. And this is really the gold standard to benchmark performance, as such, manufacturers should qualify their products to this standard to ensure that failures don't occur and the design life is maintained. So we encourage you to expect compliance to this standard when dealing with a manufacturer. A structural design should consider the load-bearing capacity of a tank. So the stronger the tank, the shallower it can be buried, resulting in reduced construction costs. But what determines the depth of cover required are things like the soil type, tank design capacities, the groundwater level, pavement thickness, and the design loads. CIRI identifies these as the main factors that are overlooked that contribute to failures. And manufacturers must be able to come clean with their strength data and prove it with independent testing. So to address all this, CIRI have detailed all the requirements for laboratory strength testing. So therefore, when considering loads, both short-term and long-term loads must be addressed. Dead loads include the massive soil surrounding the structure, plus the weight of any slabs or anything else that's permanent that a tank may be subject to. Live loads are temporary loads, things like vehicles, which also need to be considered. And tanks that have vertically aligned load-bearing pillars will offer good vertical strength and stability. And manufacturers should be able to provide you with independently tested vertical load results. However, lateral loading is just as important as vertical loading, as it takes into consideration of the soil mechanics. And this is a key driver on how deep a tank can be installed. Be aware that specifically in high water table applications, tanks can be pushed out of the ground. So in these instances, either locate the tank close to the surface to avoid the water table or beneath a heavy pavement to help anchor it down. Great emphasis should be placed on the jointing methods and systems that use a combination of cross bonding and brick bonding allow for a more rigid tank construction. And again, manufacturers should provide independently tested and certified lateral load data. And this is to justify the installation depths that they recommend for your project. However, some manufacturers have a tendency to only disclose the short-term and not the long-term test results for their tanks. Products need to be able to sustainably support loads over the design life of the project, and this is crucial for a durable installation. Tank materials are liable to creep, meaning that they deform over time, and products must be strong enough to be able to withstand this. And long-term strength test data allow manufacturers to determine the design life of their tanks. Not appreciating long-term strength can have extreme consequences. Look, and this is an example of where an installation of where the tank has failed because of creep. And really, it's everyone's nightmare, and it just highlights the importance of long-term strength. And here's another one, not a sinkhole, but an actual tank failure in Pittsburgh, Pennsylvania. So taking a tank out of a controlled environment like a laboratory and measuring behaviour in a typical environment gives all stakeholders better indication of performance. And while CIRI provides a methodology behind laboratory static tests, ACCO conducted a full-scale live load test on one of our buried tanks to an American standard. And this was documented by the Ohio University. Equipped with sensors to measure vertical deflection and lateral movement, the tank was installed as it would be in practice. So here's a short video of the test. So it was a 15 cubic metre 3-layer tank, which was backfilled with soil and finished with a layer of asphalt. The objective was to measure the structural responses under a static and dynamic live loads. And a 27-tonne truck was used for the test. So the first step was to excavate and level the foundation. Tanks were then assembled adjacent to the excavation. Then a total of 14 potentiometers were installed inside the assembled structure to record the vertical displacements or compression. And then, as it would be the case with a typical OSD tank, the structure was then wrapped with a geomembrane. total of 8 vibrating wire soil pressure cells were placed beneath, around and on top of the buried structure to record pressures that develop in soils adjacent to the structure. And to finish off, the tanks were then backfilled. Then also compacted. And then asphalt rolled on top of the tank system. So during the test, a truck was driven numerous times to simulate the dynamic loads would be experienced in practice. So a total of 23 load tests were conducted. And the truck was also parked for a period of time above it to ensure the static load requirement was met. The results were all collated and the university compiled a report. Now, the deflections the structure experienced under live load applications was less than 0.06, and this is far below the allowable deflection limit of 5% set for buried polypropylene drainage structures in the AA-SHTO bridge specifications. So during the repeated heavy static load applications, the structure remained the most of the load-induced deformations through elastic rebound upon unloading. So overall, the Stormbricks SD structure proved to be rigid with elastic properties, stable and strong. If you would like to read a summary of the report, you can download it from the address now shown on the screen. And as there are no Australian standards governing the strength of plastic underground stormwater tank systems, we've teamed up with Engineers Australia to detail everything you need to know on the topic. And this is so you can integrate tanks into a project properly without the risk of tank failures from either short-term, dynamic or long-term dead loads. If the URL on your screen is too long for you to write down, it'll be sent to you after the webinar. For tanks, the hydraulic capacity refers directly to the volume of water that a structure can store, and different tanks in the industry will of course offer different capacities. You can optimize the capacity of the tank by selecting products with high void ratios, which is over 90% for geocellular systems. Having such a high void ratio reduces excavation and obviously the construction costs because of that. Now, arch systems, just for a quick comparison with geocellular systems, have a void ratio of around 50%, which essentially means the excavation needs to be almost twice the size. Arches hold water in the open space beneath them, as well as in the voids above them between the stones. And this isn't an efficient way to hold water, not to mention the additional costs of the stone fill. So on the screen, you'll see an example of two tank systems side by side offering the same amount of storage. And as you can see, the installation volume of the geocellular tank is considerably smaller. As another comparison, let's look at concrete structures. And although concrete tanks provide 100% water storage inside the tank, they do have thick walls, which reduces the void ratio to around 80%, and they are expensive to build and also to install. In comparison, geocellular tanks are more economical while still providing high amount of storage. For concrete pipes, they're obviously round, but they need a square trench, and each pipe needs about 250 mil approximately of sand or stone bedding in and around the excavation required. Means more fill material, making the installation bigger and more expensive. But a good manufacturer should be able to help you to optimize the space while helping you meet the storage volume requirements of the project. A tank that's versatile enough to shape itself in and around your project will give you more options to meet the site's storage requirements. Modular tanks offer the ability to adapt themselves to the underground space with some level of flexibility. This is particularly useful when avoiding things like existing services, buildings and structures or footings. And manufacturers should give you tank layouts which help you navigate the physical constraints of your project, as well as clear installation instructions. And as I mentioned earlier, tanks can perform any or a combination of these roles. And depending on how a tank is used, it requires a different type of wrapping. In non-sensitive retention or detention applications, geomembranes are used as a bladder for storing water along with the geotextile on the outside to protect it. Now, as long as minor leakage from the tank can be tolerated, the membrane is normally just taped together, and this is used on the vast majority of applications. But for sensitive applications, like a tank positioned close to a building or simply to contain contaminated runoff, we would recommend using a welded geomembrane installed by an accredited contractor. And this ensures the water tightness, but as before, the geotextile wrapping on the outside, though, needs only tape to secure it. And the focus on the integrity, this is the focus on the integrity of the membrane. And for infiltration systems, there's no membrane used, just a geotextile which acts to minimize the sediment buildup within the tank while allowing the water to percolate. Now, stormwater tanks can be very large, and moving them to site and then into the excavation can be costly. So geocellular plastic tanks are lightweight to transport. The modules are designed to stack inside one another, which means that they take up significantly less space than other products. And this leads to fewer trucks on site and fewer trips to the excavation area. Not only is this more cost effective, but better for the environment. And the site itself should be considered when selecting a product. The time it takes to store and assemble these tanks can significantly affect construction costs. Some tanks need storage, and worse still, some tanks simply don't stack. Some plastic tray systems are generally assembled away from the excavation area and then lowered in, and there are additional rent and labour costs associated with building and storing the tanks before installation. Geocellular stackable tanks, however, are really beneficial for sites, particularly with restricted space or labour, in that they can be built inside the excavation area and quickly. So to get access to a tank, a dedicated entry point for both inspection and cleaning is needed, like the inspection chambers shown on the top right. For inspection and maintenance, open cellular tanks provide uninterrupted access from one cell to the next. This is in stark contrast to a closed-in structure, say, of a typical crate system. A tank that can't be maintained serves really no purpose, and cameras and jets must be allowed to pass throughout without restriction. And here's just a short video showing how a camera was used to inspect a geocellular tank under a pedestrian precinct. You can see the camera move through the system easily without being restricted by any physical barriers in the tank. And at the bottom left, you'll notice a chainage counter showing the distance travelled by the camera from the manhole. And so we've come to the end of our presentation, but to summarise, these are key things to consider when specifying tanks, from compliance to legislation, the tank's design and strength, and void ratios, and how easy it is to transport and ease of access, inspection and maintenance. This now ends the formal part of our CPD. But a little bit about us. These are our products for our external applications. We offer trench drains designed for buildings, urban and civil infrastructure projects. And ACO Access is our range of manhole covers, and ACO Cable Mate is our range of cable pits. Our own Geocellular tank system is called Stormbricks, and we have two versions, SD for vehicles up to 9 tonne and heavy duty for vehicles up to 30 tonnes. And details of this product range can be found at our website. These systems can be sized using a Storm Updated program by Cleans Water and Music program by eWater. To help you manage surface water for your projects, whether it be up to collect, clean, hold or release, I like to say that we're here to help you across the board with all our products. AskACO.com.au is where you'll find all our free project services, and these are designed to complement your own project-specific calculations. You can also email us your project requirements or even ask for a simple question to askaco.acowas.com.au. As part of our suite of services, we can help you with storage above or below ground. So where the consequences of ponding of water on the surface are low, we can provide ponding analysis when temporary ponding can be tolerated. And we do this deliberately by undersizing trench drains to restrict the flow. Or alternatively, we can help you remove the water entirely off the surface with adequately sized surface and subsurface drains. For your specific projects, this involves us configuring both trench drains and tanks and providing you with a part schedule for that configuration. And we can also provide Syria-based structural tank calculations. To make the structural validations process easier, we've designed a simple online calculator built around Syria. And all you need to do is provide some basic information relating to your project. Then you will receive validation on whether the tank is strong enough. If the results show the tank is overloaded, the parameter requiring change will be highlighted. For instance, you may need to bury the tank a little deeper. So here's just a short video of the software. So after you have registered or logged into the program, click on Start a New Project at the bottom of the screen. Fill out the project details. This project will be saved under your login name and can be viewed or revised at a later date if required. Once submitted, at the top left-hand corner, you'll toggle metric units to Syria Guide for Australian standards or Imperial AHSHTO, which is for the North American market. To start, simply select either Stormbricks SD or HD, the number of layers, and enter the project's cover depths and the water level details. For environmental conditions section, select the live load pavement type, the soil type from the drop-down boxes, and that best describes your tank in your project. And this will pre-fill the fields below. This is all the inputs that are required. Click Next, and it will take you to the results page where you can download a summary report or a comprehensive report. The summary report contains the project details and a list of all the inputs on the first page. The second page contains a summary of the results. The comprehensive report contains the detailed structural calculations over the 4 pages. If you'd like to talk to us directly, we have technical representatives across the country who would only be too happy to assist you with your next project. So thank you so much for your attention today. I feel quite privileged to be able to share the space with Troy and the team and to speak to you. I'll make sure our post-webinar email to you contains all the links necessary for you to learn more or simply reach out to us when you need to. So I'll now hand you back to Amanda. Thank you.
Hi, a big thank you to Troy and Greg for their presentations. It's now your turn to get involved. As always, please ask our speakers questions via the chat box and who your question is directed to. And thank you for everyone who submitted questions while registering. I'd also like to welcome Darren Chen, Brand Manager for Civil Construction Products, who will also be joining us for the Q&A session today. I'd like to start with you, Troy. We've had a question that's come in from Michelle, and Michelle is watching from WA. Good afternoon to you, Michelle. Asking you, Troy, What are your thoughts on practitioners looking at underground storage solutions for capturing major events, 1% AEP and above? Troy.
Okay, yeah, look, usually the Casino Authority will ask to capture up to that and including that 1% AEP. Now, for anything rarer than that and beyond that, engineering-wise, it can be done. That's not a problem. It does require quite large storage areas and also larger infrastructure to convey these flows. So, to be honest, a lot of the stormwater management is seen as a burden already on very heavy constrained sites. So, I would hate to see the need for underground storage of these rare events to sacrifice some of the other water cycle management aspects. Personally, when we look at these more rare events, the focus should be on minimizing the risk to life. So for sensitive uses, childcare or aged care or along those lines, there might be a need to have that as an underground storage. For other aspects, it might be focusing on evacuation routes, refuge. So there might be some opportunities to utilize some above ground storages for places where they're probably not going to be accessed during a high intense storm event, and really leave the underground storage to do the day-to-day running of the rest of the stormwater management. That's my thoughts on that.
Thanks. Thanks, Troy. Thank you so much. And staying in the West, we've had a question from Jamie. Good afternoon to you. And Jamie, this question is asking firstly to you, Greg, and then maybe Darren, you can add your input. And Jamie is asking us, standardisation of underground storage with minimum design expectations, load requirements, ability to clean, inspect, etc. Greg, your thoughts?
Yeah, thank you, and thank you, Jamie. Look, I think there is a need for standardisation probably across all those topics. Really, standardisation for structural requirements, in particular, as there is no standard in Australia. So, as I've mentioned, Syria is the best standard to utilise. So, I think some standardisation there. And a lot of the feedback from clients and councils has been around the structural integrity of these units, how units are maintained. So having some standardisation around the systems should be free for inspection through the pillars, should be able to have access points to be able to clean and maintain the systems, and then also be measured against some standards like Syria. So, yeah, I think it's a really important point, and probably something that needs to continue to develop. We need some standardisation. Darren, is there anything you want to add?
Yeah, definitely we need standardisation. It just gives, I suppose there's a lot of products that are out there on the market, and how you differentiate one product from the other. So if you've got a standard that all manufacturers and suppliers can be measured against, then it's good for the designer. So then you've got one sort of yardstick and benchmark to compare the products against. So in Australia, as Greg said, there is no standard, but UK have their construction industry research and information association have developed a standard for geocellular tanks, and listening to our guys in Europe, our colleagues in Europe, that there is going to be a European standard coming out, a Euro norm. So we'll be waiting to see when that comes out. We'll be measuring our products against that, and hopefully all the other manufacturers, importers of these products will also do the same, and then it'll just make it easier for all designers to specify and implement these kind of systems.
Thanks, Darren. Thanks, Greg. And just a reminder to everybody out there that this is our last Thought Leaders webinar for 2022. So please keep those questions coming. Troy, just bringing you back into the conversation, we've had a question coming from Shu, who's actually overseas, asking you, what is the recommendation to link the system to respective stormwater systems in buildings? Troy.
Okay, I hope I'm understanding what you're referring to as linked. If not, let's blame the Socceroos for that. But basically, we have our downpipes and our pits and pipe network that collect the storm, however you want to do it, and they drain to our respective storages. Ideally, there would want to be a first flush or pre-treatment in between that. They'll enter our storage system. Now that could be a combined retention detention. So that might be in parallel where we fill the retention that spills into a detention that freely discharges, or it could be a combined system where we have the lower section, the storage and reuse, and the upper active free space really for detention. And then it's just a case of having a pump, whether it be to a header tank or direct to the source, that can go to our reuse capacity. So really for an underground storage, it's no different than a traditional rainwater tank or stormwater system.
Thanks for that, Troy. We've had a question come in from Louis, and Louis is based in New South Wales, asking you both, starting with you, Greg, and then Darren, asking, what advantages does the product offer over the local competitors?
Yeah, thank you. As I mentioned in my presentation, there's underground tank systems and there's underground tank systems. So the key thing what you need to be looking for is, from an ACO perspective, we have a Geocellular open system throughout the tank. So it means you've got clear access all the way through to be able to see if it needs maintenance and be able to put a camera down and through it. Where we compare other geocellular systems, like I mentioned, a typical crate system. If you've got a box with 4 walls, how do you then get a camera down and through that, and then not only be able to visually see if it needs to be maintained, but then how can you either flush it through to be able to clean the system if you can't get access to it? So I think in terms of maintenance, that's definitely one. And then, as I also mentioned, there's a lot of systems out there that haven't been tested correctly, or they don't specify all the long-term loads, just short-term loads. So really, from an ACO perspective, we have systems that can be structurally verified, and also systems that can be maintained and then also easily assembled on site to reduce those assembly times as well. So it's a complete, I think there's more than one aspect you need to look at, but across the board, it's a system that's well suited for underground geocellular storage systems.
Darren, do you want to add to that?
Yeah, definitely. I'd like to add. I suppose with the ACO system, where we weren't the first in the market, we learnt a lot from the existing products in the market, and from the early beginnings where these systems were designed. They were more like, as Greg said, milk crate systems, where or flat pack systems where you just build all the walls, tops and base, and you're just building boxes, and you stack the boxes on top of each other, connect them together and put them together. So what we learned, and from listening to the designers and the asset managers, that access and maintenance was a big issue with these kind of systems. And because you can't get into each individual box and clean them out, the design has a very limited life. So once it fills up with silt and dirt, there's no possible way of getting it out. So what ACO have learned, we built these systems with these pillars within the system, so you can get around between the pillars and to clean them out. So access and maintenance was one of the things that we looked into a lot, and we provide access shafts, and you can put in access to clean them out very easily. You can send some high pressure hoses in there, get a vacuum truck and suck out all the water, clean them out, and then you can put a camera down there just to inspect it to see if it's all the silt's been removed. So with that, with the pillar system, it also provides strength, as Greg said. The pillars act like columns, and they're very strong. And as with all the ACO products, as you can see, we've done a lot of lab testing, and we've also done in situ testing to back up our product.
Thanks, Darren. Thank you for that. Coming back to you, Troy, we've had a great question that's come in from Paul, and Paul's in Queensland, And he's thinking about the budget. So the question is, Troy, how are stormwater asset managers communicating the costs of storage and ensuring budgets are established with adequate provision for its inclusion? Great question. Troy.
Yeah, that is a good question because, yeah, the proprietary products, and I'm sure they got a lot of data on the terms of supply, install, and maintenance. But it's fair to say that a lot of the designers, when we come to it, will design, ensure it's constructed right, and then we sort of walk away. We don't often have that direct connection with the asset managers. So the information isn't always readily available. It is out there, but it's something you definitely need to go looking for. Look, it is relying on some of the manufacturers to supply some of that, and also to some of the contractors in terms of costings. Alternative to that, there's council, strata, having direct conversations with those, but also it's important to understand that it's sort of one size fits all is not the case here. We really need to look hard on what the catchment is, understand that in the design, and really just apply best practice. So yeah, it's a very fair question, but it's not always the easiest answer.
Okay, thanks very much. Thank you for that. Staying in Queensland, we've had a question for you again, Troy, from Pradeep. Good afternoon to you. Asking, in Queensland, we are vulnerable to droughts, which are likely to frequent. We need to seriously look at town planning and land development throughout the state. In southeast Queensland, a few years ago, the dam level went down to 22%. We need to create lakes in coastal areas. Whether this option was this option ever looked at? Troy, big question.
Yeah, completely. And I sort of started to touch on that, I guess. With all these floods and a lot of rainfall we're having lately, it is easy to forget that this rain could stop. And then we're really having an issue with burdening our dams and whatnot. So I guess we have to ensure that a water cycle isn't reactive. We have to sort of consider all the climate scenarios there when we just do determine our management system. And it's not a case of one or the other. There is a place for retention and detention, and they aren't interchangeable necessarily. So when we're having high rainfall, we really don't want to start dewatering some of these storages, because when that rainfall does stop and that storage has been emptied, then we don't have access to it. Likewise too, when we don't have the rainfall, we don't want to start suddenly using our detention and flood mitigation methods to hold the rainfall, because when this rainfall does start up again, we won't have any active storage. So I can't speak specifically for the options that were investigated there up there at South Queensland, but I can say that when you're looking at a regional strategy, or even just a site-specific strategy, I guess looking at capturing that on-site reuse on-site and looking at some of their water demands will really reduce the burdens on some of our traditional dams. So it's really just important to ensure that our water balance does consider some of the drier periods and test that and look at the demands and potential supplies and sizing the management strategy accordingly.
Thanks, Troy. Thanks. A great answer. Greg, back to you. We've had a question come in from Giovanni asking, will new systems replace unsightly water harvesting tanks? Your view, Greg.
Yes, thank you. Look, good question. There's actually a couple of things that come to mind with this. Look, certainly from an aesthetic point of view, yeah, absolutely, you can move. I'm assuming you're talking about above ground storage systems. So look, you absolutely can move it underground. But the other aspect of moving the tank from above ground to below ground is not only aesthetic but also utilisation as well. I know a couple of large commercial businesses that would otherwise have large tanks above ground, but that also takes up areas for either utilisation for other things or car park spaces. So moving it underground has advantages of not just from an aesthetic point of view, but also from a utilisation point of view of the existing pavement or area.
Thanks, Greg. Darren?
Yeah, I can add to that. I suppose with these tanks, these can be installed underground, these geocellular tanks, and then you can put landscaping on top. You can put parklands. You can put car parks. So it makes use of the land above, and the tank is hidden below. So yeah, majority of the time you'll be using specifying these in landscaped areas and under car parks, those kind of applications.
Thanks, Darren. And Darren, just staying with you, we've had a question come in from Vishwanand, who is also watching in New South Wales, asking, can you talk a little about how you cover cleaning maintenance of the underground storage system, Darren? Yeah,
with underground storage systems, in Troy's presentation, he talked about pre-treatment. So there's all different types of pre-treatments. What you wouldn't want to do is just have raw stormwater going straight into these tanks. That means they've got to be fully maintained then. So what you'll have as a pre-treatment upstream from the tank is either silt traps, sediment traps, GPTs, put stormwater filters, all the different types of pre-treatments that are available there. And it really depends on the environment, I suppose, where what's being picked up, and you'd specify or design a pre-treatment that would get those, I suppose, trying to get rid of what you're trying to prevent from going into the tank. So what you're letting in is probably only very fine silt at most into your tank, and then that will allow you, these tanks will have access shafts that allow you to get access from the surface, and then you can, as I said before, you can get a sucker truck with a vacuum pump and just suck all the water out, get an inspection camera in there, have a look around, as long as there's access through the whole tank, and that's where the ACO Stormbricks system comes into its own with accessibility. And then you can send down a high pressure hose, break down the silt, fill up the water tank a little bit, then suck it all back out, and then inspect it again. If it's all clean, then it's ready to go. So that's how you'd maintain the ACO Stormbricks tank.
Thanks. Greg, have you anything to add there?
No, that's spot on. I think the whole system needs to be considered from pre-treatment devices all the way through to the tank system.
Thank you. Another question's coming from WA from Glenn to you, Troy. Glenn's asking us, how do we keep water quality good in underground domestic tanks?
Okay, well, that probably starts really at the construction phase, because once construction material sort of gets in a stormwater network at all, then you're forever chasing, trying to improve that water quality. So it's a matter of just understanding how the construction methodology is going to work, try to bypass that wherever possible. Then in the operation phase, well, stormwater harvesting is great for improvements to the receiving water. If you're looking to improve the water within the tank itself, well, then we're coming back to that pre-treatment and understanding what the catchment is, because the treatment for a pure roof area to one that is receiving surface water, they can be slightly different in terms of pre-treatment, but it's really critical to ensure that we have the pre-treatment and then the maintenance regime that keeps up. And that's really the only effective way to maintain a good water quality in the tank itself.
Thanks, Troy. Thank you for that. Back to WA, we've had quite a few questions from there, and from Helen. Good afternoon to you, Helen. Asking you, Greg, and then maybe Darren too. How has material life and end-of-life management been considered for the long term? Greg.
Thank you. Look, it's often a question that gets asked around the material. Look, polypropylene, recycled polypropylene, has a long design life, so that is an advantage. But the material is only as good as a design of the system around it as well. So while polypropylene is a good long life material, and particularly it's buried underground, so it's not subject to all the temperatures above ground either. So good design life, but it's also important that it's in combination with a very well designed product that's been tested both in laboratories and then also in situ as well. And in terms of end life, look, it's a good material because it can be recycled as well.
Thanks, Greg. Darren, do you want to comment on Helen's question?
Yeah, look, with polypropylene, that's what we use to make our Stormbricks tanks. We use a recycled glass fiber content in it, and as Greg said, the end of life management will involve just recycling material, dig it up, and polypropylene is easily recycled.
Thanks for that. Just staying with you, Greg, we've had a question coming from Matthew, and Matthew's watching from South Australia, asking you, Greg, how are plastic cell storage solutions maintained and cleaned of silt and debris? Greg?
Yeah, thank you. Yeah, it seems to be a common question and I get it too from designers, clients, councils. It's about how do you it's almost the number one question, but it's either two things. It's either how do we maintain it and the structural integrity of the unit are almost the two most common questions. So to be able to maintain a system, number one, first thing, it has to be able to get maintenance to it, be able to do that. So on our systems, with a maintenance shaft or an access point, you can remove the cover, and then either the system can be flushed through and jetted through, or also you can use a suction truck to then suck out any silt. And having an access point, it's also in terms of what maintenance regime do you put on a system if you can't see inside of it. So being able to have an access point, not just be able to clean it, but also to see inside of it, so you can have a maintenance regime to be able to put that in place. So I think it's important. You can either jet it out, suck it out with a vacuum truck, but there's also other configurations with a system that's quite versatile. You can incorporate things like silt bays into the tank system as well, so all the silt falls down to a low point. So it makes it a lot easier for access as well. So there's certainly different ways you can achieve that. But number one, before you can do anything, you must have an access point and be able to have clear access right through the tank system.
Thanks, Greg. Darren, do you have anything to add there?
Yeah, look, I think this question comes up a lot because the stigma of plastic tanks from the very early designs. So the very early designs, as we talked about before, is the crate systems, and a lot of councils and other asset owners have been stung using these kind of systems, and if they can't be maintained, then their lifetime is cut short, where it's not functional anymore because it's filled up, it's clogged up, it's blocked up. So I suppose there's a lot of new manufacturers bringing new technology, new designs in that allow for access and maintenance more easier. But I suppose it's trying to get back to see these asset owners and explain and show them how they can clean these systems, these new systems.
Thanks, Darren. Thank you for that. Troy, we've had a question coming from Ray, asking you, Troy, should we be aiming for retention basins with extra capacity instead of detention basins? I think a retention basin would provide better environmental outcomes. Thank you, Ray.
Yeah, look, it's a fair comment. Retention does provide great environmental outcomes when you talk about managing stormwater volumes. The issue comes when we have high storm events like we are now, and the retention systems are full. As they're not free draining, they remain full during a storm event until they're reused. So oftentimes when the peak comes down through there, these systems are already full. So there's no active storage, meaning there's no management of the excess flows. So why retention are great for those environmental volumes and whatnot, they don't manage the flooding and peak flows storm events. So short answer is we require both.
Okay. Thank you for that. Thank you for that, Troy. I just want to sort of take a bit of a pause here on our Q&A and just ask our speakers that, obviously we are seeing a lot of changes in the weather, etc. And what do you see, starting with you, Troy, as the key themes coming through or the key trends for the next 5 years in this industry, in this sector?
Yeah, look, climate change has always been a pressing point. So sanity checks on potential climate change risks is always something we need to consider when considering stormwater drainage design or stormwater storage. The other aspect is really these environmental flows. More and more times, we're not just looking at those peak storm events and managing those. We're looking at managing volumes, and that's where the retention comes into play. So you'll see more and more onus on managing some of these where detention will create a lag, and the receiving waters are subject to a lot longer flows than naturally. We'd like to see a lot more in the terms of the volume management as well.
Thank you for that. And Greg, what's your prediction? What's coming down the pipe?
Well, and I touched on a little bit earlier with some of my comments, but I think as a manufacturer that manufactures surface drainage systems in the way of channel and grate systems, which convey the water, and then how do we manage it sort of downstream from that through underground geocellular systems. I know certainly over the last couple of years, it's more and more. If I did a presentation, a few years back talking about climate change, obviously it's got some merit, but a lot more merit now. So more and more I'm seeing how do we deal with the water at surface level. We're seeing a lot more centre barriers. We're seeing a lot more retrofitting of channels, trying to make sure that we design to higher storm events. I've definitely seen that trend as well. And then the complete package on then how do we deal with that water after we capture it at surface level, and how do we deal with it downstream, whether we want to use it for potential retention or infiltration. But Troy really touched on a good point as well, and he's right. It seems like it's never going to stop raining at the moment, but we have come through some severe drought. And if we look at the US has been going through it, so they're almost on the opposite side of what we're going through now. So you don't want to be pessimistic, but I'm sure our turn will come. So then it's where we need to plan for not just the now, but also the future. So putting in detention tanks or water reuse and being able to use those systems so it has less load on dams and things like that, which was in some of the questions that was in the Q&A. I think having that forethought now is really important. So as a manufacturer that work really closely with clients and designers, that's where I'm seeing quite a large increase in that space on how we deal with it and dealing with a lot more of it.
Thanks, Greg. That's great. Thank you for that. Stefan has sent through a question, staying with you, Greg. You talked about your calculator, and Stefan's asking, does this calculator have the ability to control the soil parameters for infiltration purposes? Thank you, Stefan.
Look, yeah, thank you for the question. Look, our calculator deals with the structural integrity of the system, not so much around the infiltration performance of the soil around it. Is there anything you want to add there, Darren?
Yeah, the structural calculator is more for structural design, not for what material for infiltration. If for infiltration, it should be really sandy soils. That's where you use it. And as Troy said in his presentation, not for clay soil. So as long as you've got loose sandy soils around the tank, then it'll infiltrate into the ground. Our structural calculator will take into account what kind of soil is backfilled around, because that will determine what kind of angle of the soil mechanics that imposes onto the side of the tank. It takes that into consideration, but not in regards to the infiltration material.
Thanks for that. Thank you, Darren. And Greg, a question that's coming from John. Good afternoon, John. Asking you, what percentage of recycled plastic is used in eco products? What are the challenges in using soft plastics? Greg.
Well, look, certainly the challenges in using soft plastics is to ensure that when you're making a product that has the structural capability that's required to take the intended loads, that the right materials are then make up that material is capable of withstanding those loads, essentially. So it's quite a, whilst its term is a soft plastic, there is, and it's a recycled polypropylene, there is fibres that help produce the material to make sure it withstands the load. So it's not, probably not in the true sense a soft plastic. It does have elastic properties, and which you saw in some of the in situ load testing. So whilst there is some small amount of deformation, it comes back to its original shape. But what we found in a lot of that testing, and that video is available on our website as well for the in situ testing, was that even though there was some very small deflection, it was significantly lower than what the accepted level was. So as a material, it's actually quite strong.
Thanks,
Is there anything you
Greg.
want to add, Darren?
Yeah, the recycled content in our product is the glass fibres. They get added in, all of it's recycled. Polypropylene, I wouldn't say would be a soft plastic, but it has got a bit of an elasticity to take loads. Yeah.
Thanks, Darren, and thanks, Greg. As always, we're starting to run out of time, and we have covered a lot today. Future of stormwater storage. What I'd like to ask both speakers, and maybe starting with you, Troy, out of your presentation, as they were at the end of the year, what are the 5 things, or a quick summary of what key takeouts you want to leave our audience with this afternoon? Thanks, Troy.
Look, all we sort of touched on is there's a need for the whole water cycle management. So that is the detention component and the retention component, and really an effective design of a management starts well and truly early days in the design to think of it all the way through. Think of the design constraints, think of some of the construction constraints, and then think of the operation and maintenance all the way through. So early on days, you really need to get your head across all of those to make an effective stormwater management.
Thank you. Greg?
Look at the complete system, I think is number one, not just look at one aspect of the underground system. And that starts from things that we're speaking about in terms of systems got to be able to have access. It's got to be able to withstand the intended load. So look very carefully at systems on what standard they're being tested to and how it's being tested, both on dead loads and live loads, long-term loads. I think that's extremely important. Systems that make sure they're versatile. Do they maximise the space? So don't just look at the cost of a unit, because some systems take up a lot of space and therefore not a lot of storage. So you want to maximise your space and maximise your storage as well. So I think that's really some of the critical points around underground geocellular systems. I don't want to steal all your thunder, Darren.
Bring us home, Darren.
Yeah, look, just want to reiterate that, yeah, you got to take all those considerations that Troy and Greg just spoke about. And look, at ACCO here, we provide a product, but we also provide support to help you specify the correct system with the right accessories, access shafts, and access covers. We can help you, size it up. We can also provide that structural calculation, which is now on our website, which is available for use to help you to confirm that what you're specifying is structurally stable and strong enough to take the loads that are going over the tank. So I'd probably just ask everyone just to have a look on our website and have a look at the video of the testing again, and what we can back up our products and the information we can support you to specify a strong storm brick system.
Thank you, Darren. And please, audience, join me once again in thanking Troy Eales, Greg Facey and Darren Chan for great presentations and taking the time to join this Thought Leaders webinar. I'd also like to thank Engineers Australia's wonderful industry partner, ECHO, for their ongoing support. As always, we'd ask you to complete a short feedback form. It takes about a minute, which is linked in the description box below, and it helps us to move forward and plan future sessions that you'd like to hear, topics that you're interested in. As we are at the end of the year, the 1st of December, I just wanted to let you know on behalf of the Thought Leaders team here at Engineers Australia that we have, including this event, 61,318 people have registered for Thought Leaders events, either online or in person. And I'd like to thank you personally and professionally for your support. It means a lot. Thank you again. We look forward to seeing you at our next Thought Leaders event in 2023. Have a wonderful Christmas and a lovely summer break. Thank you and good afternoon.